So, hi everyone. Thank you very much for this invitation. It's for me a great chance to for me to hear so many talks about quantum vortices evolving in 2D. And I learned a lot of things, and I'm pretty sure that there will be some place where we can interact. So I'm very happy about this meeting already. Indeed, I'm going to talk about visualization of quantum vortices in helium-4. And you will see I will not, all my talk will not be in 2D. You will see there will be 3D, but it's interesting. Also, I would like to take the chance to say that in this amphitheater 6 years ago, Dan Lathrop, who I'm sure you are aware of their seminal work of visualizing quantum vortices in helium-4, confessed that they could not see their vortices again. And one of my messages here will be that we are able to do it again in Grenoble. And I think this is a good thing for the community. So a very quick introduction, because we already heard about helium-4, but it's a very, very nice fluid that has a very peculiar phase called helium-2 when you go to low temperatures. This fluid has many peculiar properties. And roughly speaking, we could say that it has a very, very, very low viscosity. It has an extremely high thermal conductivity, and it contains quantum vortices. Quantum vortices in helium, as it already has been said, has a core size which is extremely small. Okay, 1 angstrom is almost the size of a helium atom. And it has the same properties as yours. That is that the quantum of circulation, so the velocity field around these objects are quantized, and here is the value of this quantum circulation. To describe this fluid, Luca already introduced the two-fluid model. I just wanted to make it very rough, fast, and without equation. I will try to avoid a lot of equation. And so we see here the density of the superfluid fraction that increase when we go from the transition temperature to extremely low temperature, while the normal fluid component will decrease. These two fluids exist at the same time. So at high temperature, this fluid behaves as a normal fluid. It obeys the Navier-Stokes equation. At extremely low temperature, it's closer to a Euler equation, not exactly that, but close to. And in the middle, you have both of these components that live together and interact through the presence of quantized vortices. Okay, this is the context. I wanted to start by a canonical flow in superfluid helium, which has already been introduced also by Luca, the thermal counterflow. So let's imagine this slide is flooded by helium-2. You put into it a pipe blocked on one side, you put a heater there, and you switch it on. The superfluid component cannot transfer heat. So what happens is that the heat has to be transported out of this pipe through normal fluid. So this arrow is in fact inside the tube, okay? And at the same time, by mass conservation, the superfluid phase will compensate for that and will enter. And this is why we call it counterflow. Vn is opposed to Vs. Therefore, this flow maximizes Vn minus Vs, and Vn minus Vs is the force with which both of these fluids interact is proportional to this value. And therefore, it generates quantum vortices in this tube. And we can quantify their presence, or what happened in this tube, by the average intervortex distance between two of these spaghettis into this pipe. This is one way of characterizing this, and this is because the circulation of these vortices, or their strength, is quantized. So now I'm an experimentalist. So this is nice, and this has been done many times because it's a relatively easy experiment to do. There is nothing moving. And you know, we are here at below 2 Kelvin, and moving stuff at 2 Kelvin is hard. So we are happy with this. But now what happens if inside such a system I put a sensor? First class of sensor is an Eulerian sensor. That means I put it at some place and I look at what happens, what's going through it. What will the sensor feel? Either Vn, either Vs, a mixture of two. It's a complex subject, and I will not cover it at all. But I just wanted to mention that we have many studies ongoing about that, because all the sensors have to be homemade, because they have to be small, because they have to be compatible with low temperature, etc., etc. And we need to do a lot of things about that. Another class of sensors are Lagrangian particles. So that means if we seed the flow with particles, and we let them evolve and we look at them. Okay, well, the same question is still valid. What will push these particles? Either Vn, either Vs, a combination of both. The quantum vortices, what will be their role? Good questions. So I had the chance a few years ago to go and work in Prague with Marco Lamantia in the group of Schrebeck, and we did exactly this experiment. So here you have the drawing of this cell. The dimensions are in millimeters. So I let you discover this. We took movies of such particles. Here they are d-deuterium particles evolving in the flow, and they are tracked. We track them optically. So the real particles are the white dots, okay? And what we see, first order, is that globally they go up, okay? So they are most likely pushed by the normal fluid. This is what we could have expected. The normal fluid has a viscosity, so there is a Stokes force that probably pushes them up, okay? But now if you look at it a bit more carefully at the previous movie, you will see lots of events like this. Look at this particle. It stops, it moves fast, it stops, it moves fast again. Okay? This is very unlikely. I mean, I was coming from the community of turbulence, pure turbulence. This kind of particles doesn't exist in turbulence, okay? And this is not an exception. There are tons and tons of particles having this kind of motion. So here is the vertical position as a function of time of such a particle. In blue is the one we just looked at. So it goes fast, it goes slow, it goes fast, it goes slow, it goes fast. And there are tons of it. To analyze this, I make a long story short, okay, for this part, because I want to talk about the rest. We are going to look at here the PDF, the double PDF of the horizontal velocity here, vertical velocity there, and in color is the probability to find this value, okay? If you look at it, then you see that there are two, it's like a bimodal motion, so there is two peaks, one which is relatively huge here at relatively small velocity, and one which is here at relatively high velocity, which is much less wide in terms of horizontal velocity. This is the debate we will have to have with Luca about the wideness of this, but these are our experimental results. So how do we interpret this? Maybe it can be interpreted as, thanks to the fact that this high velocity peak very well corresponds to the normal velocity that we can expect from historical work and theory. This one, the lower one, is probably part of the phase space where the particles are trapped, or at least cannot move freely within the flow, because most likely of the presence of quantum vortices with which they interact along their motion. This can be backed up by a hand-wavy argument that on top of this PDF, the red arrows here are nothing else than the acceleration of this particle conditioned by the velocity. So I take a point there. It has an horizontal velocity. It has a vertical velocity there. If I sort all my particles and I say, okay, all the one which has this couple of values here, I compute their acceleration, I can plot this acceleration, and it gives like a motion in a phase space, Vx, Vy, of these particles. And so what we can see is that you can go from a trapped state to an untrapped space if you are free to move, to accelerate fastly in the straight direction. And then when you are in this state here, if you bump on something, your velocity will change and you will fall back into this trapped state. The thing is that the thing is that the norm of this acceleration are compatible with what you can expect concerning the force acting on the particle in such an environment. Okay, if you take delta being the average vortex spacing that we know, and the size of the particle, you can compute the force, and acceleration is a force, then you can come back to this acceleration. and this is roughly compatible. But here we haven't seen any vortices. We may have seen the fact that particles interact with vortices, but we didn't saw them directly, okay? And this is probably because we are in a turbulent state and that our particles are shaken a lot. And therefore, they get trapped, untrapped, trapped, untrapped, and this is a complex system, which is very interesting to study, and we will go on. But for now on, I want to simplify, at least in the mind, the problem, and I want to consider a very simple case, which is a rotating fluid, a rotating superfluid. So what happened in the case of a classical fluid if we make it rotate? It's not a test, I give you the answer. The fluid will, after some time, rotate as a solid body inside its container. The surface will be parabolic, and the velocity field is defined here and is defined everywhere. What happens with helium-2? Seen from the far, the same thing. It's a little bit deceiving, but that's the case. But if you zoom in, the quantum vortices have to align themselves with the axis of rotation, so in that case vertically, and arrange as a lattice, a regular lattice, very similar to the Abrikosov lattice in superconductors. And this lattice can, of course, be defined by, again, delta, the intervortex distance. To make both of these visions compatible, we can compute the circulation of the velocity field. In that case, it's pretty direct. If you take this contour here, the velocity field is collinear with this contour, so the computation is direct. In that case here, we will use some kind of Ampere theorem, and we will count the number of vortices that cross a surface that is attached to this surface, okay? Multiply it by the intensity of the vortex, which is the quantum of circulation, and this gives, very simply, this expression there. If you say this equals that, you get the so-called Feynman rule that relates directly the intervortex distance to kappa, the quantum of circulation, and omega, the rate of rotation of your platform. So this has been observed experimentally in the past, first by Yamchuk et al. In a group of Packard that was cited in the talk of Nina just before, where they observe from the top with a revolutionary technique, I would say, for the time, this lattice appearing, the faster, so this dot here is the trace of a tracer that impact on a photo. And the faster you spin, the more vortices you see, okay? And they look like they arrange very well as the lattice we expected. Secondly, in 2006, during the PhD of Greg Bewley and a group of Dan Lasrop, they managed to decorate quantum vortices with hydrogen particles, and they had this nice picture. In that case, the rotation vector is vertical, so I hope you agree with me that we see vertical lines there, and this was, for me at least, the beginning of a new era in this field, because we can hope to track these vortices dynamically, because we can here make movies. Here, the time of acquisition was very long, I would say. But there was some caveat, I would say. In this experiment, okay, first it took a very long time to arrive to this point. Second, they put some honey into their helium. So of course you cannot put honey, but they put helium-3 into their helium-4 to increase the viscosity of this fluid and stabilize their system. But also it took 3 PhDs, okay, to arrive to these pictures. And here, they never managed to, they didn't manage to have quantitative results about that. Okay, they have very nice picture, and this is brilliant. This was a seminal work, and without that, nothing else could have happened. But there was not a lot of quantitative thing, and in particular, this fundamental rule was not checked. And also, reproducibility is an issue. Therefore, I started my research project a long time ago in the Institut Néel in Grenoble and built up a cryostat meant to do that and meant to do most of the things we could imagine. So this is the experimental cell that contains the superfluid helium. It has 8 windows looking at the center of this cell through different angles. The idea here is to be able to have any possible optical diagnostic that you can imagine coming from the hydrodynamic point of view, so 2D measurement, 3D measurement, PIV, LPT, whatever, anything you want. It's complex, okay, but theoretically we can do that experimentally. And everything was optimized. Everything was optimized. I could just give you one number. The average losses on this cell is 100 milliwatts, which is very little for such a big device. And the idea here is that we wanted to control everything we do inside this cell, and that it's not heat leaks or defects of the cryostat that would conduct the flow that we study inside the cell. Okay? So as an abstract, it's a complex aquarium that allows for eventually 3D visualization. Since the time is counted, I will not give you the full story about how it works, but it's, I think, interesting for anyone to know how it works, because it's complex, and it explains why systematic studies are hard to do, because they take time and etc. But I just want to mention there is in fact 2 helium reservoirs. Of course, there is also liquid nitrogen to thermalize the thing and make it better in terms of autonomy and control. So this is another liquid helium reservoir, not the one that we use for experiment, but we have a cold valve that we can open during the experiment to fill this. I keep you this. Just check that this is a temperature as a function of time, and the scalar log, and this is uncommon, but in that case, it's the only way we can do. So when we do that, here we only have liquid helium at 1 bar pressure, which is at 4.2 Kelvin. This is not helium-2, this is helium-1, the normal fluid. So if we want to get helium-2, we need to pump here. If you want to pump and do it seriously, so the idea is to go from this point on the liquid vapor equilibrium to somewhere here, okay? You pump, and you want to do that in a controlled fashion. There is a very small schematic here, it's not even complete, and in French, yes. But look at this picture. This is how it looks like in real, okay? And so you can imagine how many leaks, how many hours to set up all this. And there is a very particular thing, which is here. The cryostat is down there, because we will see in the next slide. This is the full view of the control room. The students are here, up there, and here is the main control of everything. Here now we have two screens to have all the values of the cryostat in live. Well, everything works, and we are happy. And so one more complexification comes from the simplification that I did a few slides ago. I told you I want to have a simple system, or a simple rotating system. Okay, so sorry, it's not exactly here. Here I can pump, I can have superfluid there, I can put particles, I can do my experiments, and the idea of all this conception is that by the end of a working day, we can evaporate all this part, and without burning too much helium, or because it's getting very, very, very expensive. I don't know if you know that, but it's starting to be a problem. And the helium that we have polluted with deuterium or hydrogen cannot be sent back to the liquefier. Otherwise, we damage it, and I get a lot of enemies in my lab. Anyway, so we can loop. But so the particularity of this cryostat is that this entire system that I told you is actually mounted on a spinning table, and we can spin the entire thing. The laser, the camera, everything. So it's mounted on a spinning table that levitates on a 50-micron air cushion. So this is to avoid any vibration, stabilizes the thing. It can rotate up to 2 hertz. We've never done that, okay? The empty table spinning at 2 hertz is scary. So with the cryostat on it, we are not ready for that. But we went up to 18 RPM, which is already quite something. Of course, everything has to be remote controlled and data logged because you don't want to sit on the table when it's spin at 15 RPM, even if we did it at the beginning, because you have to, but now it's okay. And we have to have this very particular thing that, for example, the experiment of Greg Bulle didn't have, is a control of the pressure as you spin. When you control the pressure, you control the temperature, you control all your system, and therefore we need to have a pumping feed through to control this temperature as we spin. And we invented this thing, and it works, and we are very happy. But it requires precise alignment in all directions, and I really, really, really thank Grégory Garde, who is hidden here, an engineer with whom I've been working for many years. He's hidden here just because he doesn't like me to show his face, but therefore I talk a lot about him. And this is a little bit how it looks when the laser is on, the cameras, etc. You need specific electronics. The optics are relatively standard. But then you also need to generate your particles. And this is where some of the secrets of making a successful experiment is. And this is done with both of these parts, one which is in the lab and which is embedded on the spinning table. To do these particles, we didn't reinvent everything. We used what was in the literature, but so that means in the papers of Greg and following PhD students. And also my collaborators in Prague, Marco Lamancia, we had lots of tries of all this. The principle is to make a mixture of, at high temperature, of a high fraction of helium and a very small fraction of the gas that you want to condense and make snow with it into your cryostat. Okay, this is easy to say. It's said all the time like this in all the papers, but there are actually tons of parameters there. And these tons of parameters are crucial. The only thing I can tell you today is that we found the sweet spot and that we are able to do nice measurements now. The experimental cell, so at the heart of all this system, you have this thing here. Inside this thing, we put a channel, about the same one as we saw in Prague earlier. So the size does not appear. Okay, it appears here. 2 centimeters in wide, and it's about 10 centimeters in height. The role of this channel is to protect, let's say, the part where we're going to do our studies from spurious flows. And, well, if everything I told you earlier was true, then inside this channel we should have quantum vortices arranged as this lattice here. So this is fake image, of course. And if you cut it with a laser sheet, like this red thing here, and look at it with a camera, you should see this kind of images, okay? So this is a real image in our cryostat. So I will call you the old results, and this is our first good results, I would say, and with different rotating speed. The images are inverted, okay? The particles are black. And I hope you see vertical lines. And I also hope that you see that if you move from here to there, the vertical lines are less and less far away from each other. So delta is decreasing. So this is indeed what we measured. This was the first measurement that we done with a ruler on the screen. We were quite happy because we just put this famous Feynman rule, and which with absolutely no adjustable parameters, and this is what we got. Secondly, I wanted to show you that we have the dynamics of this thing. So this is where we are here in 2D, and we will leave 2D very soon. But here, I just show you that we have the dynamics, so you could see the particles were going up a tiny bit because we are using dihydrogen particles, which are slightly less dense than liquid helium. So they move up, they settle up. You could also see eventually that there was a small motion like this. This is due to the inner container of the cryostat, which has a 50 micron oscillation due to all the mechanics. But I hope you will let me live with this 50 micron oscillation, considering that the experiment is 3 meters in size. Okay, and moreover, we see that the structure was fairly stable. So to go more serious than a ruler on a screen, we used a wavelet in order to measure this intervortex spacing, wavelet algorithm, just to have it, let's say, an objective measurement of this. And this is what we got. It gets, okay, the error bars got smaller, but also then we figured that this formula here is the full black line, and it seems that we are more on the lower one. And this we could explain, I think, fairly well by saying that there is no reason why we would cross with our laser sheet and depth of field the lattice in a particular direction, okay? So if you cross it in the blue like this, in the blue configuration here, you get the perfect rule. But if you cross it like this with a pi/6 angle, which is the biggest one you can get, then the projection of this lattice gives you this there, and we are fairly happy. Okay, so to reach this, we had to analyze lots of data in order to have error bars, to be certain of what we were saying, and etc. So this was the system. We had the pipe here. We were looking in this region of interest there. And at the bottom of the pipe, there was in fact a heater that for now was totally off. Okay. But now what happens if we switch on this heater and we send a sine wave into the system? So it will throw a pulse of normal fluid upstream and excite the lattice. And as you've seen here, the vortices start to dance. Okay. So here it was a movie. We'll see a better one at the very end of the talk. And here is a time-space evolution of the very same movie. So if you take a line here, you put it there, and then as time evolves, you just pack the images. Okay, so we see here the small oscillation I was talking about, 50 micron oscillation. And starting there, we switch on the heater, we see an amplification, and we see waves appearing. If you want to follow me a bit, I want to see also in these images something which is very nice. If you follow, for example, this trajectory here you see a particle that is in focus and goes out of focus, then it goes in focus, and then we lose it because it goes up. But this is for me the trace that this is an helix that we are looking at, which is what you expect for Kelvin wave or inertial waves. And this is indeed what we are studying right now. This will be my biggest equation, but I will only talk about the drawings. If you search the total relation dispersion of a wave in such a system, you will find that there should be three main components. Inertial waves, which happen in normal fluid when it's spinning, okay, which is a very peculiar kind of wave. For instance, the group velocity is orthogonal to the phase velocity. I mean, lots of funny things like this. You have Kelvin waves, which are the waves that you expect on the vortex, which is lost in the middle of the universe. And Chachenko waves, which are the waves that you expect on a vortex in the middle of a vortex lattice. Okay? So now our ambition is to try to analyze this seriously, let's say, varying all parameters possible, and see if we can address this relation dispersion. So to do that, we've been trying many things. Tracking is not too bad. Maybe we'll come back to it with a full tracking of lines, etc., but it's hard technically, so we didn't manage so far to reach this level. So we use PIV. PIV with a relatively big window, so that we get those velocity field. Actually, this is the same velocity field, but filtered at different frequencies in the Fourier space. Because if you look at this relation dispersion, I discarded the Chachenko wave for now because orders of magnitude, calculus of orders of magnitude tells me that it's probably not the case. So here we have inertial wave, the relation dispersion of inertial wave, combined with the k-square of the Kelvin waves. So this gives these networks of relation dispersion as you evolve from 2 RPM, 2 rotation per minute, to 18 RPM, which are the ones that we measure, okay? So if you look at what happened at excitation equals the rotation speed of the experiment, well, it's 0.5 in this notation here. And, well, there shouldn't be any differences in the wavelengths that we measure here. But when you go to sigma equals 1, here you see there is starts to be a difference between the different curves, okay? And this is hopefully the first point of this measurement here, because here it's relatively clear that we have a well-defined wavelength of about, let's say, 2 millimeters, which for now roughly corresponds, but I will come back later with a more precise measurement and more variation. Okay, this was all for the waves, but we are very excited about that. And now we can go to a different regime, which is if you put heat, but you put a lot of heat, okay? And there, what happens, this is a different camera, this is a high-speed camera. You see that we are able to destroy the lattice entirely and trigger tons of reconnections, or at least strong interaction between the vortices. And we end up in a flow where the particles are not trapped anymore, like at the very beginning of the talk, okay? In that case, it's the same experiment as in the beginning of the talk, except that we are now spinning, okay? But at the very early stages, we can see lots of vortex-vortex interaction. And this is, of course, very important because it's, this reconnection plays a key role into the dissipation of these fluids, and we intend to study that more precisely in the future, but we probably need to change a bit the optics and the camera, because you see the images are less nice, but this is because the pixels on the camera, on a fast camera, are much bigger, therefore we lose resolution and etc. But at least we can do that ever and ever after, and I wanted to show this in big, because you probably heard about vortex-vortex reconnection, but if you look in the literature, there is, I don't know, less than 100, I think, that have been reported, and in this movie you will see much more than that. So I am happy to show you all this in one slide. Lots of reconnection, and maybe the most important part is that in that case, we are starting from a well-known and controlled initial condition, and we know what triggers this reconnection, which is not the case in any other movie of that kind. But it requires more work. So with this, I arrive to my last few slides, that we have a lot of work to do because we need to explore all the frontiers between all these regimes, okay? So this is, I would say, fairly well established now, and this is our initial condition for studying waves and for studying reconnections, or at least vortex-vortex interactions. But this was a shortcut because there is more space, and the phase space is bigger. Okay, we have omega, we have the heat that we introduced in the system, but we also have the temperature, and the coefficients in the vortex equation are temperature dependent, and we intend to go and see if we can test all this in this system. And we need to establish also the frontiers between all these regimes. Well, this was, to study all this, we built up a collaboration with Pierre-Philippe Cortet in the FAS, who is an expert in inertial waves, and who already helped us quite a bit in analyzing our data. Giorgio Kostolovic, which does lots and lots of simulation of all kinds in these systems. Juan Ignacio Polanco in Légy in Grenoble, who just got hired as a CNRS researcher, who also work in numerics, and myself. And this defined a path, hopefully, to quantum turbulence that we intend to explore in the next few years. But we have lots of work to do, but I wanted to thank all the students who have participated in this adventure. Some of them have already moved, and some have, one is finishing his PhD, and one is just starting his PhD. This is why the square here. And I thank them for all their help. And with that, I finish my talk.
Thank you, Mathieu. Do we have a question?
Hi, thanks, very nice talk. So you can say that the inertial waves are just for the normal part of the fluid and Kelvin waves for the superfluid, or not?
No, you cannot say that. The inertial waves will affect the quantum vortices, definitely.
And another, if I can. It seems from the movie, but I am not sure, that the particles do some clusters. They come together.
Yeah, this is one difference with the previous observation. Is here it's even more is even clearer that indeed they looked at the decoration. So in previous results, people were very keen on saying that the particles were like a netless pearl on the vortices, very well with a well-defined length between them. Well, this is not our case. This is all I can say. This is clearly not the case. This is an experimental fact. We need to understand that maybe, but for now, we're happy with this very nice movie. So here, the difference with the previous one is that we have a much thinner laser sheet, and therefore, nicer movie. Because one of the goals that we have now is, instead of working in 2D like we did, is having this thin sheet and making it scan through the volume faster than the dynamics of this wave, so we can reconstruct the 3D motion of this entirely. And for instance, one thing would be to see if this wave, if this helix spin in the direct or indirect direction with respect to the rotation of the platform, which is one characteristic of the Kelvin wave, for instance. Should spin in the other direction. And here you see that, I mean, you see like lasers coming up, okay? This is coming from the fact that the vortices are going out, coming back in, going out, coming back in. This is much clearer here. And you also see that there are particles in between the vortices. And, well, with eyes, I would say that they do follow. I mean, they have the same motion. Maybe we can analyze that a bit better, but order 0.
So I'm really amazed by this image. It's really nice. I don't know if you can get some 3D in the future, I mean, like with multiple cameras. My question is, if you stop the rotation immediately, can you create anti-vortices as well, or you just...
So yeah, if we can spin one direction or the other, it would be the same.
No, I mean, it's rotating, then you stop rotation.
So we did that. There is almost an entire PhD on this kind of experiment, but at that time we were not able to decorate the vortices. We were playing with deuterium particles, bigger particles. But what I can tell you is that when you stop the, so we intend to study the transient states. This is what you're asking generally. But it's difficult because the cameras are spinning at omega. So as soon as you change omega of the platform, the fluid will not react instantly. And this is, in fact, what you want to measure, what's going to happen. And therefore, there is a funny motion happening. I mean, funny movies, I would say. The first movies we saw like this, we call them stargates, because basically all the particles go away from the center. And this looks funny, but it's just an effect of the fact that the camera end plane, where you look at, doesn't spin at the same velocity as the system that you're studying. Okay, so you see a projection of the velocity, which does that. So hopefully we will manage to do that.
Cameras are not on the same platform.
They are on the same platform, but when you change the velocity of the platform, the fluid will take time before adapting to that. So during the transient, you're not spinning with the vortex.
Okay, so we have time for this last two questions, and then we'll have to...
Can I just get clarification? What temperature are these experiments at?
Sorry?
What temperature are these experiments?
Sorry, I didn't mention. Good question. So for now, most of the results are very close to T lambda. We are 2.1 Kelvin, but we have some unpublished and test lower temperature. The cryostat, in principle, can go down to 1.2 maybe Kelvin, where you have already 90% superfluid, but still it's harder to have nice decoration. So for now, we work where we are safe.
The reason I ask is because, I mean, I tend to think of Kelvin waves as excitations on a vortex. If you're at such high temperatures, then there's a significant normal fluid component present still. And then I'm wondering whether, I mean, seems to be like just sort of sloshing around caused by the normal fluid dragging the vortices around. But I would regard as sort of true Kelvin waves would be highly damped by the mutual friction coefficients that would be so large, essentially. So
for sure, they are at much lower amplitudes than that.
Yeah, so I'm just wondering, I mean, whether they would even follow a dispersion relation of a Kelvin wave for these excitations. It's not.
We will discover that in the thorough analysis of our results. But the fact that we saw something at sigma equals 1 in the data, which is absolutely invisible with eyes. Actually, it was a surprise. Okay, and it's indeed an amplitude which is 10 times smaller than the sigma equal 1/2, is already a sign that probably there will be. I mean, this can only be the sign of Kelvin wave, in fact, because at sigma equals 1, inertial waves do not exist. It's normally okay. So we will see. But I think there is a hint.
Okay.
But I agree with you. This is why inertial wave, I mean, relatively often when people see something like a wave on something like that, they call it Kelvin wave. I have my doubts.
Okay, last question.
Thank you, very nice, very, very nice. So do you have an idea how fast are the particles? So how well they follow the vortices? They are inertial particles, no?
Yeah, this is of course something that I never mentioned, but don't forget that my particle, I mean, I didn't say it, but my particles are 10 to the 4 bigger than the vortex core, okay? They are 1 micron particles. So as long as, when concerned about the Feynman rules, well, now we've checked it, it works, there is nothing to say anymore, okay? And it's relatively static in the rotating frame, so they don't play a big role there. But for waves and for reconnections, they will play a role, and it will depend on the temperature and all this, okay? But as you know, I've worked with inertial particles some of my career, so I hope we will be able to handle that. But don't worry, I'm not forgetting that, even if I forgot to say it.
Okay, thank you, Mathieu. So thanks, Mathieu, again.